So anyway, the space weather is what you're seeing here. That's the sun. The sun is very non-uniform, and this is a cartoon, of course, is an artist rendition, but we will see real images soon. And sometimes there are these eruptions that there is a chance always that they can arrive at the Earth and interact with the Earth environment. So all this link of things from the sun to the Earth is space weather. That's what we will be studying in the next months. So then I think I move on now after the movie. So there is importance of space weather comes from the fact that it has a number of impacts. So first of all, it's a natural phenomenon that eventually leads to these northern lights that you see here on the top left. But it has impact on many technological infrastructures. Bad impact. It's a damaging effect. It can affect space communication. It's very dangerous for humans in space, and perhaps the most important impact that it does, it damages the long conductors, so pipelines and power grid. There are scenarios where power grid can be disrupted for many months. That's in the worst scenario case, which has never happened yet, but there's something to prepare for. And then a more controversial issue is whether this sun-Earth connection has an impact on the Earth climate. We will have a lecture about that towards the end of the classes. It's a more controversial issue, of course, but it's interesting to know what are the long-term effects of the sun on the Earth and whether they may have any impact on the climate. So this worst scenario case is linked to this famous event that happened in August and September of 1859. So this was a series of eruptions. What you see here is the drawing that was made by the person that observed it. The name is Carrington, is kind of the first famous solar physicist in history. So in 1859, there were, of course, no telephones, no power lines, but there were the telegraphs. And what you see there is the disruption of one station, the extra currents that developed in one station of the telegraph. And some of the telegraph lines caught fire and the stations had to be repaired. So in 1859 already had a big impact, but of course there was a minor aspect of their life. Is now if the power grid were to be affected now, the effects would be tragic. So here is a study that was done a few years ago of what would happen if the Carrington event were to happen again. And it was said that the impact would be tremendous for the economy. As you can see here, $2.6 trillion was the estimate of the cost. But the most damaging thing is that it will leave people with electricity for several months, because it's not so much the power line in itself, but it's the transformers, the big transformers on the biggest power stations. They need to be reconstructed from scratch. It's not something that you order from a catalog. It has to be built for the specific case. It's not a general tool. So it takes several months to build one. And so if more than one is to be replaced, it will take months to rebuild them. And people will remain without electricity for all the period. So that's something to prepare for. Belgium probably is not in danger because this happens at northern latitudes, more like in the UK, Sweden, Norway, and then in the northern parts of the United States and Russia. Belgium is sufficiently further down the latitude that we shouldn't be affected, but unless it's even worse than the Carrington event. So the Carrington event is expected to happen every 100 years. They call it, there is like a big storm once every 100 years, and then there's even worse once every 1,000 years and so forth. They do this analysis also looking at other stars and see how often they have these huge eruptions. So it's expected that there should be one like the Carrington event every 100 years, but there are even worse happening every 1,000 years. So that's what we have to prepare. Okay, so I will now, I will give you this overview. I will suggest some references for what we will be using during the course. So there's this nice book that is available at the library. And I like it because it describes space weather, but it describes also the physics behind it. And then there are all the slides that I present, and also the other people will be presenting will be on Toledo. Some of the slides are already on Toledo, so you can already see the future classes. And then there is a course notes that were uploaded on Toledo, and some other material like some photocopies of this book and other books. It's also available on Toledo. So all the material is there. So let's start with the sun. So this is the sun. That's the origin of all the effects that we see. Of course, the energy of the sun comes from the middle, from the core, which is extremely hot, and that's where nuclear fusion produces energy. And then there is a radiation zone where the photons produced by the nuclear fusion uh, move out as kind of in a diffusion kind of radiation format, but it's a streaming of energy. And then there is a final region, the convective zone, where instead energy is not um, radiatively going out, but it's a convection. So it's like boiling water. It forms a layer of plasma. So this is very energetic state of matter where the electrons and ions have separated. So the atoms have been not break in the sense of a nuclear reaction, but break in the sense of removing stripping the electrons from the nucleus. This extremely hot region as internal motions that bring the energy from the radiative zone to the surface. As you can see, as you go from the center to the outside, the temperature decreases from 15.7 million degrees in the center to 7 to 2 in the radiative zone, up to the surface, which is at about 5,778 Kelvin, which is hot, of course, but there are many activities on Earth that are hotter than that. So the surface of the sun is fairly cold if you, I mean, you know, in a stretch of imagination, but if you look at the internal working of a melting pot where they produce where they melt iron and carbon to produce iron, it's hotter than that. So it is a relatively cold temperature. We will see in a moment that as you move out from the surface and you go towards the atmosphere of the sun, it's much hotter, and that's one of the biggest puzzles. But the other thing that we need to know about the sun, which is really the main driver of space weather, is the fact that the sun does not rotate uniformly. So it's not like the Earth that rotates as a solid body. The sun does not rotate as a solid body. The equator rotates faster than the poles. As you can see here at the equator, the time it takes for one single rotation of the surface of the sun is 25 days. But as you move up into the latitude, it's become 26, 28, 31, and then the pole is rotating only in 35 days. So this differential motion is called differential rotation, steers everything inside the sun, because it's like you're mixing with a spoon, and this mixing produces creations of magnetic field and all sort of releases of energy that eventually lead to these big eruptions. So the differential rotation is a critical aspect of space weather. It's kind of the origin of everything. The differential rotation and these convective regions where there are all these motions that produce the magnetic field of the sun. Okay, so let's start now with looking at the surface of the sun. That's how the surface of the sun looks. There are two different type of regions. You can see there are all these basically cells, which are the convective cells, and you can think of them as when you see boiling water, there are bubbles on the surface of the water. Here are the bubbles on the surface of the sun, and that's a convective cell. So that's where the energy is coming up from the interior. But besides the convective cells, there are these dark spots and bright spots. So these are called they're called sunspots, and that's where the activity is happening. So the sunspots are basically the driver of space weather. All the eruptions and releases of energy happen around the sunspots. But there are regions also that are brighter. So in fact, when the sun has more sunspots, overall is emitting more energy than when there are fewer sunspots. And that's because the loss of energy, the reduced amount of energy that is coming out of the black regions, so the black regions are darker and so they emit less energy, is more than compensated by these brighter regions that instead produce more light. And so overall, when there are a lot of sunspots, there is more total energy being emitted from the sun. There's something to remember when we're going to be talking about climate impact, because of course, if the sun is very active, it emits more light, more energy, and that can have an impact on the climate. So this is the photosphere. It's a picture from 1992. This is visible light. So that's taken, of course, with filters. You should never look at the sun. This is always done with instruments that filter, I mean, they reduce the light so you can see better the spots. Here there are many spots, and here you can see the spots moving. And following these spots, you can see the differential rotation, because you can see that the spots in the equator move faster than the spots at higher latitudes. So this is a blow up of one of these particular regions. So this is taken from ground telescopes in Sweden. What you see here is the black spot, and you can see all these stripes. They're coming out of the sunspots. That's the magnetic field. So you really are seeing the magnetic field lines. Imagine that this is like a magnet, and then there are the traces of the magnetic field lines that come out of the magnet, and they form all this region around the black spot. It's called penumbra, this region, where it's not as dark as the interior of the sunspots, but it's darker than the surrounding. And then you can see all the convective cells of the convective motion from the interior. And notice in between the convective cells, there are these brighter regions where more energy is released. So that may be part of the mechanisms that have to do with the heating of the surface of the sun, or the atmosphere of the sun, that we will see in a moment. The atmosphere of the sun is much hotter than the surface, and perhaps what you're seeing here is energy being released, energy that then heats the atmosphere of the sun. For reference, this is the size of the Earth. So the sunspots are really big, are bigger than the Earth. Okay, so this is a couple of sunspots. Now we are looking at the magnetic field. So when you look in visible light, this will be dark, and this will also be dark. But what you're looking here is the direction of the magnetic field, the intensity of the magnetic field, and its direction. So when it's black, it's coming into the sun, and when it's white, it's coming out of the sun. So these are two sunspots. One is positive magnetic field, and the other is negative magnetic field. This is a measure with, looking at the polarization of the light. You can detect the magnetic field intensity, and this is called a magnetogram. And you can imagine that there are field lines coming out of here and entering into the black region, and so you can imagine there are all these field lines going from one side to the other. So that's how the surface of the sun really looks when you look at the magnetic field. Okay, so that's the field lines I was mentioning. So you are seeing now a different wavelength. So let me go back. Here is this instrument. This data is coming from a spacecraft called Solar Dynamic Observatory. It has been around already for a few years, and this was a revolutionary mission. It had much more resolution than anything before, so it allowed us to see the sun much more clearly. And this HMI is one instrument that produces the magnetic field information. The next picture instead is the AIA. It's another instrument that looks at the sun at different wavelength. It's 171 nanometers. And you can see the same sunspots. But in this particular choice of wavelength, you can see the magnetic field lines going from one side to the other. And you can see how these tend to form this arch, which sometimes is kind of a line along a certain direction, and so it's called an arcade. So these arching structures are the structures that sometimes erupt and release energy towards the Earth, if it is towards the Earth. I mean, sometimes it's toward Mars or some other planet, but there is a chance that it's towards the Earth. So those are the structures that kind of the driving mechanism for spaceflight. So where is this magnetic field coming from? Just briefly, the origin of this magnetic field is the differential rotation. So the fact that the sun has a differential rotation, imagine there are some magnetic field lines inside the sun. As the differential rotation keeps steering, always faster in the equator, it tends to stretch this field line and stretch it and winding around the sun, so it produces energy. It's like a dynamo, like the dynamo of the bicycle. The motion of the sun will constantly pump energy to the magnetic field. And then sometimes this magnetic field from the interior erupts into the surface and forms these arcades. that we were seeing. And that is why two sunspots always have a positive and a negative one, because on one sunspots, the magnetic field lines are coming out, and in the other sunspots, the magnetic field lines are coming back in. So that's the structure of the sun magnetic field. Much more complicated than the magnetic field of the Earth. That is a simple dipole. The magnetic field of the sun is much more complicated. So here is the progressing picture that shows a magnetic field lines being steered and steered and steered and then causing the eruption. So that's the origin of the sun's magnetic field, the differential rotation. Now we go out of the surface of the sun and we look at the atmosphere of the sun. So this is a picture again from a combination of an eclipse. During an eclipse, this was taken, and the outer part is from an instrument called LASCO. This is another spacecraft, it's called SOHO. It's an older spacecraft with less resolution than SDO. But unlike SDO, also takes images away from the surface of the sun. So it sees a wider range. And the inner part here that looks like an eye, that's the eclipse. This is a picture taken from Earth, from the ground during an eclipse. So here is the moon that blocks the sun, and you can see there are these bright regions here. It's called the chromosphere. And then you see the corona around it. So it's called chromosphere because it has a color. In Greek, chromo means color. So that's the origin of the name. And then the corona around it because it's like the crown around the sun. And it has this very typical structures that are like pointed hats that reminded people back when it was discovered to the helmets of German soldiers. This is German soldiers at the time of the, not Second World War, I mean, in the 1800s. And they had these pointed hats with the spike up on top. You may have seen it in historical movies back at the time of Prussia and so forth. So they call them helmet streamers. And it's still called helmet streamers from the helmet of the German soldiers. Although nobody has seen a German soldier with a helmet anymore, but the name stuck from the 1800s. And these are structures that are very typically present all the time on the sun. And then there are regions where instead it's just streaming out. So there are these helmet streamers like here, and then there's this region of open field lines. Those are called coronal holes. So they're like holes in the corona. Basically the sun energy can stream out freely. There is nothing limiting it. While in the helmet streamer, there is this pointed part. So energy is kind of contained in the helmet streamers and remains closer to the sun. Okay. So as I mentioned, there is, as you go up from the surface of the sun, you first encounter the chromosphere, then there is a narrow layer called the transition region, and then finally the corona. Okay, so that's the real puzzle. As you are in the chromosphere, so that's the lowest part of the solar atmosphere, you see that the energy starts to go down. So as you move from the surface of the sun, it is fair to assume that the temperature will go down. As you go up from the Earth and you fly on an airplane, you see the temperature outside drops. So as you are away from the surface, the energy tends to drop. But then it starts to grow, and it grows dramatically in the transition region. And it keeps growing in the corona. So the understanding of why the energy is released and how and it produces this heating is still not understood. There are various theories and there are models, but it's an open question. What is it that produces this tremendous heating? As you can see, it's tremendous because it goes up into 2 orders of magnitude and more. So here you have temperatures of millions of degrees, while here it was 5,000. So there is a tremendous heating. And that is probably linked to wave activities and to what we were seeing in the previous slide. Go back to these structures that you see here that are releasing energy, probably. And there is a new instrument that just came online a few weeks ago in Hawaii that is measured these structures much more clearly. And so hopefully there will be progress in the next months and years in understanding what are the structures that you see between the convective cells. So let me go back to the temperature of the corona. The structure of the overall magnetic field of the sun is like this. This is an idealization. We saw the picture of the eclipse earlier. The Helmut streamers are not so nicely located always at the equator. But say the idealization of the magnetic field of the sun, sorry, is that it has the Helmut streamers on the equator and the open field lines, the coronal holes in the two polar regions. So that's kind of the most idealized situation, but in practice, it's never so simple. But that's kind of a way to visualize it. So let's look now at the arcades that are the central driver of space weather. So a little bit more realistic picture is that the equator is tilted, the Helmut streamers are not at the equator, but rather tilted. These are conditions that are typical during what is called quiet solar period. Below instead is what you see when it's active solar period. Right now we are in a quiet solar period, so right, the sun looks like this. But a few years ago, it was during the active period, and the sun will look more like this. So there are Helmut streamers all over the place, sometimes even near the equators, and the coronal holes can be even at the equatorial region. So it's a complete mess. And it's imagine this three-dimensional. One can visualize these Helmut streamers as being a belt around the sun in quiet times, but in active times, it's a very three-dimensional structure with variation also around the sun, which of course we don't see. We don't have any way to know exactly how it's going around the sun because we see a two-dimensional image. But the guess is that the structure is very complicated as you go around the sun. Okay, so now I'm going to show you some images that are the instruments. So that's the overall magnetic field of the sun, taken on from SDO, the Solar Dynamic Observatory. That's the best instrument available in space, with some positive and some negative regions. And I can, as I remind you, there are these magnetic field lines going from one to the other. This is another type of instruments that's on the ground, less resolution, but also gives you the magnetic field of the sun. So the other images that are very typically done is the following. It's a very important language. So I wanted to introduce it at the beginning because when you read anything about space weather, these names come all the time. So you have to consider that the Earth is going around the sun. So when we are seeing the rotation of the sun, we also have the revolution of the Earth around the sun. So the time it takes for one point to come back in our line of sight depends on the rotation of the sun, but also on the motion of the Earth. So the rotation of the sun on itself, let's say the pure rotation is called sidereal. Sidereal means with respect to the faraway stars. The synodic means that it's what is seen from the Earth. So the synodic rotation is different from the sidereal rotation. Sidereal rotation is 25 days. The synoptic rotation is 27 days. These extra 2 days are due to the fact that in the meantime, the Earth has moved. And so we will see the same point again 2 days later because the Earth has moved around the sun in the same direction, by the way. The sun rotates in the same direction as the Earth. So there is this thing to keep in mind. And that all this goes back to the Carrington. So Carrington introduced the synoptic coordinates. And when you look at the sun, since we are on the Earth and is a very important point of view, he introduced a coordinate system that is with respect to the vision from the Earth. And it's called Carrington rotation. Carrington rotation is one full rotation seen by the Earth, is the synoptic rotation. It's also called Carrington rotation. And the Carrington coordinates are these. So the Carrington longitude and latitude, this is how this is done. This is basically like a Mercator map of the sun. Like when you have America here and Europe here and Asia there and Japan is out here and Australia here, that kind of map, but it's of the sun. And the way it's done is that every day you take a slice of the images that you see and you report it one next to the other. You do this for all the 27 days of the Carrington rotation. And at the end, you have a Carrington map. The Carrington map is from 0 longitude to 360 longitude and from latitude minus 90 to 90. So these are the two poles. And that's the magnetic field that you see in every slice is 1 day. So in some pictures, they show the longitude, and below it, they put the day in which the data was taken. So this is a blow up. And you can see here you have the sunspots, and you have the regions of negative and positive magnetic field. So this is a kind of map that the professional and the space weather use to make predictions. And as you can imagine, it takes 27 days. So here was taken 27 days before this data. Of course, the sun in those 27 days have changed, but we don't see it. So, I mean, this map is kind of an average over time with every region taking at different times. So you have to keep in mind that probably in the meantime, things have changed. There may have been eruptions, and if they went on the back of the sun, we had no way of knowing. Even on the sides, you know, that the magnetic field is not measured so well. The reason why it's done this way is because we have an accurate determination of the magnetic field in the center, but as you move towards the pole or towards the limb, so this region is called the limb, the side of the sun is called the limb. See here, you hardly see the magnetic field here. It's not very well measured. You only measure it correctly and precisely in the center. That's why they construct a map like that. And then, of course, we don't know anything about the back. The back may have exploded, and we wouldn't know. This is another visualization, which is kind of filtered. So let me go back. So here you see the magnetic field is rather complicated. There are very many structures with fine details. That's the surface of the sun. As you move away from the surface of the sun and you move up, the magnetic field becomes simpler. So there is one distance from the surface of the sun that is called the sun source surface. So the source surface, which is used as a standard way to quantify the magnetic field of the sun further away from the surface. So that's by tradition, let's say, by standard, 2.5 solar radii. So that's 2.5 solar radii from the center of the sun. So it's 1.5 solar radii above the surface of the sun. By then, the magnetic field is much simpler. You see the structure here. So this is done by extrapolation. This is not a fact. This is it's a theory that produces this magnetic field. It's not observed directly. It's induced from the surface magnetic field. And now this is typically the source of models of solar wind and space weather. People use this type of information as input for their models to determine what is going to happen at the Earth. So that comes from the Carrington map, and then it's extrapolated at the source surface, and it gives the magnetic field. And here you see the variation in the magnetic field from 0, which is 0 magnetic field, to positive and negative magnetic field. And curiously, blue means positive and red negative. Okay, from this analysis of the magnetic field, people discovered that the magnetic field of the sun has a cycle that lasts about 11 years. So these are the sun taken from 1996 to 2006. As you can see, there are periods where it's kind of quiet, and then periods where it's very active, and then it's kind of quiet again. This 11-year cycle is called the solar cycle. During this cycle, the polarity of the magnetic field inverts. So here, the north was positive and the south negative. Then it goes through this complicated region. Now here, the magnetic field is a big mess because it's all over the place. And now back here, it's opposite. So if here was positive, now positive is below. And if it was negative, now negative is above. So it switches the magnetic field every 11 years. So to go back exactly where it was, it takes 22 years. In 22 years, it's again positive above and negative below. So it's a very regular change in the magnetic field every 11 years. The reason why it's so nicely constant, unlike the Earth also flips the magnetic field, but over very regular periods. It can be millions of years, or it can be 10,000 years in between a change of magnetic field of the Earth. Because the motion inside the Earth are complicated and slow, is the magma in the mantle under the surface of the sun, of the Earth, that produces the Earth magnetic field. But here is the differential rotation. So it's a very regular and dependable mechanism that produces this magnetic field with a regularity of 11 years. So here you see periods of quiet and then more active over the 11 years. And this is the magnetic field. As you can see, during quiet time, the magnetic field is kind of small. Then the magnetic field becomes more intense and it forms all these regions of opposite polarity. And then it goes quiet again. So that's the then the magnetic field overall is this one. During solar minimum is nicely divided in between positive above and negative below. So in between there are the Helmut streamers. One is solar maximum is very complicated. And even at the source surface, this is the source surface, the magnetic field is much more complicated during solar maximum. Okay. So this kind of summarizes what I said, that there is an 11-year cycle, but really to complete the flip and then flip again, so that you return to the initial condition is 22 years. During the active times, it's called solar maximum. During the more quiet times, it's called solar minimum. During solar maximum, the magnetic field is very complicated, and during solar minimum, magnetic field is much more simple. Now, it's interesting to look at all these indices. The sunspot index, one of the reasons why it's interesting is also because the world repository is in Brussels at this team here, SIDC, in Brussels. I invite you to click on the link and look at their website. Here I report a few pictures that are from the website. Here is their pictures from the recent times. This is the number of sunspots per day in yellow, and then the monthly average, and the monthly average is smoothed. As you can see here, there is the 11-year cycle. There are periods of low number of sunspots, and then during the solar maximum, there are many sunspots, and then again minimum. Right now we are at a minimum, 2020. So the number of sunspots are small. So here is a bit of an older picture, but it shows the decay of the last cycle and the forecast for cycle 25. They call it cycle, from the first cycle was the first measured by current. So there's cycle 25 is now the 25th cycle since Carrington introduced this notation. Cycle 25 will peak of maybe 2025. And this is a prediction made with models of the magnetic field mechanism inside the sun. You see how that tends to have two peaks always, two peaks. This, of course, is a forecast, and who knows what is really going to happen. We have to live until 2025 and wait and see. But these predictions are not very accurate. As you can see here, there is the range of predictions. Some model predict that, and some other model predict that. So in between, there are many various predictions. So it's not very accurate. Okay, so here is the last cycles since the space age. So starting the space age with the launch of Yuri Gagarin into space, that was 1961. So it was around here during a relatively quiet time. Landing on the moon, 1969, was during solar maximum. That's the explosion of the Challenger in 1986, and the space station now. These have been the peaks. As you can see, the peaks are way not uniform. They are far from always being the same. So there is an 11-year cycle, so they are all 11 years apart from each other. But then each cycle is different. These three cycles were strong. This one was very strong, but the last cycle was unusual. So the last cycle is weaker than all the others. But the most important thing you may notice here, how long the distance from here to here. So this period of very long minimum lasted more than normal. I remember when it was 2009, and so people were starting to say, well, there is something really weird happening on the sun. See, the minimum here is much more minimum than the others. There were really months and months and months with zero sunspots, not a single sunspot. And it should have picked up earlier. It should have started earlier. And instead it kept going down. Then eventually it started having sunspots again. But there was this period here where there were conferences organized and people were worrying about what is happening to the sun. And I will come back in a moment. You will see why people started to worry about that. Because if you extend a historical period, you see that there are sometimes peculiarities much worse than this. But now the question is this a very unusual cycle, the beginning of a change, or we will go back to the normal? It's hard to know. We have to wait and see. But this was a very peculiar cycle. So that is, so space weather in the last decade, since 2005 and so, has been weak. Because even during solar maximum, it was very weak solar maximum. Here we have the whole historical record. From the time of Carrington, but before also, people started measuring the sunspots. Of course, it's not very reliable data from the 1700s. Before the 1700s, the data is taken from proxies. So they have ways to look at the level of radiation in trees and in the ice in Antarctica. And from that, they can detect what was the activity of the sun. Okay, so this is not the same type of information. This is actually been measured by people looking at the sun in blue and counting how many sunspots there are. This instead is induced information from looking at ice cores and rings in trees and stuff like that. So it's less reliable, but still it's the best information we can have. So all the last cycles, first of all, I mean, it's interesting to notice that since the time of Yuri Gagarin, the cycles have been somewhat stronger, except for the last one that is not on this map. But before, there were periods where it was somewhat weaker. But there was this very famous period called the Maunder minimum. Maunder is the scientist who discovered this minimum, where supposedly there were essentially no sunspots for decades, like almost 100 years. So the sun must have been very inactive during this period. And it was also relatively weaker activity during this period. Now, the interest about this picture is that the years of 1600 to 1700 and 1750 are remembered as the Little Ice Age in Europe. It was also affecting the rest of the world, but of course, at that time, Europe was kind of the center of the world power. So remember from the European data. There are images of like Flanders with a lot of ice, always people skating around the cities. In the Flemish painters, so those years were extremely cold. And maybe there is a link then between the solar activity and the climate. Now you can see that more recently, the solar activity has been stronger. So some led to say that, you know, this increased solar activity also increased the temperature. Anyway, that's a very controversial issue. The last solar cycles here are repeated. And as you can see here is a nice feature. When a solar cycle starts, the sunspot starts to develop a high latitude. So here we have latitude and year. The first sunspots observed are observed at a high latitude, like 30 degrees north and 30 degrees south. And then as the solar cycle progresses, they migrate towards the equator. So this is called a butterfly picture, the butterfly diagram. And it's always like that. Always the solar sunspots start to emerge at mid latitudes and then they migrate towards the equator. Okay, so here is kind of a summary of all the data with this Maunder minimum and the temperatures. And so here I put the company that is sponsoring the research to disprove human impact on the weather. But it's a very controversial issue. We will have a class about this later in April or May, where we are going to discuss the relative influence of humans and sun in this business. Yeah, it's a very active area of research, of course, and it goes beyond just looking at the Maunder minimum, but that's kind of the first indication that maybe there is some link between the sun and the climate. These are the pictures from the Flemish painters of, I think this is supposed to be Amsterdam, all under ice. Okay, so after the surface of the sun and the atmosphere of the sun, we have the solar wind. The solar wind is, this I think is supposed to be, no, movie is not. Yeah, I wanted to see, this is, I'm going to launch a link. Do you still see this?
Yes, Johnny, we can.
Yeah, okay. So that's a prediction that is made now. So this is a prediction center from the National Oceanographic and Atmospheric Administration in the United States, and it's going to predict what the solar wind will be in the next days. As you can see, it's very smooth and nothing particularly interesting happens because we are doing solar minimum, so there is not much activity of the sun. But this is a model of the solar wind, and you can see many features in it. You can see this type of spiral in motion that is due to the fact that the sun shoots the solar wind out. So there is like this wind coming out of the sun because the sun is so hot and particles get transferred out of the sun. And but this motion is linked also with the rotation of the sun. So it's often compared with this system to water your lawn that has these rotating arms that shoot the water out. And as you look at them, it forms this spiral around it. So it's called the Archimedes spiral from the mathematical formula that was due to Archimedes. So the Archimedes spiral is the structure of the sun, the solar wind. And that's due to the fact that as the solar wind is emitted from the sun is also rotating. So you see this typical motion. What you are seeing in this picture is the Earth. The Earth is in green. The other two dots is a space mission called Stereo. Stereo was launched from Earth, of course, and one was launched in this direction and the other one in the other direction. But this one was launched in that direction because it has already gone all around. So these two spacecraft look at the sun, and they were supposed to give us information about the sun at different angles. So we don't see the sun only from the Earth, but also from these two other spacecrafts. So there was a period where the spacecraft were in the back, and we could see them. One of the two, unfortunately, died at some point, and it was then briefly recovered, and then it died again. So one of the two is not working, but the other one is working, and it's still working. So we can see the sun. Now, I don't know which one to do. Maybe the red one is still active. And you can see the sun from this angle now. But last year it was here, so you could see from that angle, and then before it was there. So these things are rotating around the Earth in the same orbit as the Earth, but at different locations from the Earth. And they will continue to do so until they work. And one of the two doesn't work already. Okay, so that's the solar wind. It's a constant wind, and as you can see, it's non-uniform. The velocity is different, and the density is different, and that depends on where on the sun is originating from. So that's the equatorial view, and that's the meridional view. So you see here is on the ecliptic. There is a variation on the ecliptic, but also if you look at the meridian, so it's a cut through here. So you go from the Earth, from the sun to the Earth, like that, and you can see here the equatorial plane in the middle, and then above and below the equator, the ecliptic, sorry. And you can see the variation of the density and the velocity in this situation. As you can see here, the velocity is lower here and much faster here. So this region is called fast solar wind, and this region is called slow solar wind. And the Earth tends to be in the slow solar wind, but not always. You can see that they predict that the Earth, let's say on the 19th or 28th of this month, will cross into the fast solar wind. And then you look at the velocity, it will go from being about 400 kilometers per second to be 600 kilometers per second. This is a prediction. You can check on the 21st whether that's really happening. They are making this prediction 4 times a day, so they keep improving them. So this simulation starts from the information on the source surface, the magnetic field that I showed you earlier at the source surface. They put it like here in the black circle, and then they solve the equations from there out and predict what the solar wind will be. That's quite an achievement that was reached in the last few years. So that's the solar wind at different times. So there was a very famous mission called Ulysses mission. The feature of this mission was that it went above the pole of the sun. So it could measure the solar wind almost up to the polar region. And he did this in 2 different periods, from 94 to 95 during solar minimum. And you can see nicely the negative magnetic field below, positive magnetic field above, and the Helmut streamers in between. So the sun was very nicely, almost textbook. Well, the unisolar maximum was very different, much more complicated, with fast and slow solar wind mixed together, and positive and negative regions of magnetic field mixed together. So that's typical of the active times when magnetic field is unisolar maximum, and it's very complicated. So into summary of these two type of winds, so the fast solar wind comes, it is believed to come from the coronal holes, while the slow solar wind is believed to come from the Helmand streamers. That's why it tends to be towards the equator. It is wherever the Helmand streamers are. The fast solar wind is steady. It doesn't change in time, and it is the same from rotation to rotation. The slow solar wind, since it comes out of these Helmand streamers that are kind of closed structures, is much more unsteady. You can think of it as almost as a boiling thing. You know, this is kind of confined, but it's not perfectly confined. So now and then there is a release of energy and residual matter, and that's the slow solar wind. It is emerging out of the Helmand streamers. The Helmand streamers would like to confine it, but they are not capable of confining it 100%. So there is a leakage, but it's kind of an unsteady process, like dripping water. The slow solar wind is less than 450 kilometers per second, while when it's above 450, it's called fast solar wind. When it reaches us at 1 AU, 1 astronomical units, the slow solar wind is denser, 7 to 10 ions per cubic centimeters, while the fast solar wind is more low density. Interesting thing and still not understood is that the fast solar wind has a higher composition of helium, while the slow solar wind is more hydrogen. Nobody knows why. The fast solar wind is also cooler. No, sorry, hotter, 10 to the 5 Kelvin, while the slow solar wind is cooler. When you follow the solar wind, it has this nice Archimedes spiral that we said before. This keeps expanding. It reaches all the planets, the Earth, but then after the Earth, all the other planets, until it reaches the solar wind coming out of other stars. So this is the overall picture of the solar system, where the region inside the termination shock is a region where the solar wind is supersonic. And then you have the heliopause, where the magnetic field, the plasma of the sun kind of stops. And it meets with the plasma coming out of, or the solar wind coming out of other stars. And the interstellar medium. Interstellar medium is made, let's say, of the combination of all the solar winds of all the stars. So let's say the heliopause is the last boundary dominated by the sun, by the particles originating from the sun. And beyond that is interstellar medium. The termination shock is when the solar wind goes from being supersonic to be subsonic. So this termination shock has been observed by the Voyager and Pioneer spacecrafts that have crossed it already. So they were launched in the 70s, and they've been traveling out and out and out and out until they reach termination shock. So there have been already 2 measurements of the termination shock in different regions, because the spacecraft went out in different directions. So that's a fact. Termination shock exists. The question is whether they've already crossed the heliopause, and I think it's still being debated, whether the spacecraft has actually left the, let's say, our solar system. We could make, if we had aliens living in nearby stars, we could make a claim that the heliopause is our boundary. I mean, inside is our domain. It's owned by the sun, let's say. The rest is kind of international waters, interstellar medium. So that is interplanetary, interstellar space. But this is overall view of the solar wind impact with the Earth. So when the solar wind arrives, the Earth has its own magnetic field, going from the North Pole to the South Pole, or rather going from the South Pole to the North Pole. You know, the magnetic polarity is defined as positive when it goes into the North Pole. That's a historical definition of what is considered a positive magnetic field. Positive magnetic field is when the magnetic field goes into the North Pole. That's entirely based only on the fact that this, it was developed in Europe. There is no other reason for it. I mean, that particular polarity is considered positive. Anyway, so that the magnetic field of the Earth shields the Earth from the solar wind. So the solar wind cannot reach us on the surface because there is this magnetic field around the Earth. And so it forms this structure, which is very typical. It has the solar wind compresses the Earth magnetic field on the day side, and it stretches it on the night side. So this night side stretch magnetic field is called the magnetotail. Tail. So it's like a dog having a tail. The Earth has its own tail, which is magnetic, and it is due to the fact that the solar wind stretches, drapes the magnetic field lines away from the Earth on the night side. So of course the Earth is rotating, but we are always looking at the side that is facing the sun. So the day side looks like this. There is this region. The solar wind is supersonic, so when it reaches the Earth, it goes through a shock. And given the side that the Earth is spherical, it tends to form this spherical shock called the bow shock. And it's called bow shock because it's shaped like a bow, like the bow of the arrow throwers in the Middle Ages. So that's called bow shock. And then inside the interior structure is rather complicated. There are these cusps. The cusps are the regions where the magnetic field of the Earth comes back to the Earth's surface. So here, the cusp is basically the two North and South Pole. Then there are many other features that Jon de Keyser will explain much more in details. But so from the bow shock, as you go inward towards the Earth, you first find the magnetosheath. This is a region of solar wind plasma. So this is basically solar wind goes from supersonic to subsonic. So this region is very turbulent because it has gone through a shock, but it's still primarily made of solar wind plasma. Then there is a magnetopause. The magnetopause is where you have a transition from the solar wind plasma to the Earth plasma. So that's plasma that has been captured by the Earth's magnetic field and it remains around the Earth. It's still made mostly of hydrogen, but there is also a significant contribution of oxygen, where the oxygen is obviously coming only from the sun, from the Earth, sorry, while the hydrogen is coming from the sun. But the particles of the solar wind get captured by the Earth magnetic field and become Earth, kind of Earth plasma, becomes remain trapped into the Earth environment. A curiosity is that the solar wind is actually relatively cold. The solar wind is at 1,000,000 degrees, okay, but relatively speaking is a few electron volts. So if you measure the temperature in electron volts, this is what you get. Here you have a few electron volts, while here you have tens of electron volts in the magnetosheath, and inside the magnetosphere, plasma is hottest. So it's about a kilo electron volt or 10 kilo electron, between 1 and 10 kilo electron volts. So it's extremely hot. And that's because it's gone through the shock. Shock tends to heat the plasma, and other mechanisms also heat the plasma around here. And so the plasma inside the Earth magnetosphere is much hotter even than the solar wind. Okay, then, but like I said, Jon de Keyser will give you many more details about this interaction. So here is a list of all the things that I've explained, repeated again. So let's not spend too much time on them. Now, this interaction is very dynamical. What I was describing here is the quiet conditions magnetosphere. So the magnetosphere, how it is when the solar wind is kind of steady and nothing is happening. But when there is a storm, that gets disrupted. So let's look at the storms now. So this is a movie of erupting sun. You can see here there are being a number of eruptions, one here, that's a big one. And another, you see still activity on the sun, various eruptions. So all these eruptions have a chance of reaching the Earth. So here is an eruption. When you have an eruption, you have this filament of plasma that is kept on the sun by these magnetic arcades that we saw. And when there is an eruption, this gets released, kind of loses confinement on the sun, and it gets explodes out. And as it explodes out, it forms this outgoing shock because it's going out so fast that it forms a shock. And then there are these regions of plasma being, there's just an explosion. So at the edge of the explosion, you get a piling up of the solar wind because this eruption is faster than the solar wind typically. So it goes faster than the solar wind and it pushes against the solar wind. So it forms a plasma pileup, but it leaves behind a cavity because it, you know, it's bringing away the plasma much faster than the solar wind. So it forms a cavity below. So this is a typical structure of an eruption, which is called in our business coronal mass ejection, CME, coronal mass ejection, which is an eruption of mass from the sun, in particular from the corona. This is a structure that is very typical. You can see here this, what they call it H alpha ribbons. So these are X-ray loops. So underneath an eruption, you will see on the surface of the sun the formation of these bright regions, are really two ribbons, two lines that become brighter in H alpha, which is a particular line of emission from hydrogen. And you also see the formation of X-ray loops. So it's very energetic and it produces X-rays. Those are features that you can see by observing the sun. And when an eruption happens, this is a typical structure. I call this important because it's a typical picture that, you know, it's our cartoon how an eruption happens on the sun. The next cartoon is somewhat similar, just highlights more what are the magnetic field restructuring that are happening. So these X-ray loops are this one here, but everything is driven by this reconfiguration of the magnetic field above the sun. So that you have like a closed field lines, and you have this ribbon that has the magnetic or rather plasma in it, and also magnetic field forming a structure. And this, to be erupted, it needs to reconfigure itself here. It's a process called magnetic reconnection. And it's a driver of this mechanism because, of course, there is gravity and there is the magnetic force that keeps the plasma confined on the sun. So some force must push it up. And the force pushing it up is this reconnection happening here that pushes this plasma out and make it go out of the sun. So when we talk about explosion and eruption, what is really happening is this release of energy here that pushes the plasma up, and some plasma also push down, and it forms these bright spots on the sun. The bright spots on the sun are called solar flares, and that's a brightening of the surface of the sun. And often this brightening is linked with the coronal mass ejection, but there are also situations where the brightening happens without a coronal mass ejection. So with not much matter being released up here, still you get energy released down into the photosphere. And in the photosphere, which is the surface of the sun, photosphere is called that as this brightening is called solar flares. I mean, these names come from the fact that people discovered things over the period of time without understanding what they were. Now we have a kind of an overall view with more understanding, it connects things, and the names though remain the name that people originally gave. So flares and coronal mass ejections are two distinct processes, but they are typically linked together by this cartoon. They are happening at the same time. So here I'm going to show real images instead of cartoons. These are coronal mass ejections that were measured in 1997 by the LASCO C3, which is a device mounted on SOHO. SOHO is a European spacecraft. It has what is called a coronagraph. A coronagraph is a camera that has a circle in the middle. It's like a closing, like it's just like a disc that you put in front of the camera to block the view of the sun. So the light of the sun doesn't blind the camera, and you can see everything around it. So that's called a coronagraph. So it's really just a camera with a disc in the middle of the camera that blocks the sun. And then you see the rest. So let me run it again. What you're seeing is a white light, and you can see every once in a while there is an emission let me come back here. You see, at this time there is like an explosion towards us. You see like a ring coming out. This is called halo CME. Halo CME. Halo CME is a CME coming towards our point of view. So the halo CME are the one coming towards the Earth. because Soho is near the Earth, so it sees this CME coming. The one going to the side instead are not likely to come towards the Earth because they are going off to the side. But the one coming at us, the hollow CME, are the most likely to reach the Earth. But these are enormous. So even if they don't necessarily come directly at the Earth, they can still impact the Earth because they are so big that they affect a large part of the solar system. So that's a coronal mass ejection in reality seen by the spacecraft. So now I'm going to show you what is the impact on the Earth. It's a little bit of a cartoon. Okay, so here is a typical series of events that happens during a big space weather event. This is a famous event that happened in 1989 and caused a blackout in Quebec, and it affected also New York State. Hydro-Quebec is the electrical company of Quebec, region of Canada, and there was a big blackout. So the first thing that happened here, you can see the X-ray emission on the sun. So you can see that there was a big spike when the eruption happened. That's the first thing you measure. The X-rays are, of course, a form of light. So they arrive at the Earth in about 8 minutes. That's the time it takes light to travel from the sun to the Earth. So after 8 minutes, you see this spike. The CME has just happened. But then the CME expands and takes about 2 to 3 days for the CME to arrive at the Earth. And that's when it arrives. What you're seeing here is the high energy protons that arrive at the Earth about 3 days later, 2.5 days later. So you first see the X-ray peak at the sun, and then you get this plasma arriving at the Earth. As that happens, there is a reduction in cosmic rays. Cosmic rays, we will have a class on cosmic rays later on, and we will explain well what the cosmic rays are. But cosmic rays is radiation coming from the galaxy, not from the sun, and from outside the solar system. And it's kind of steady, but when there is an event like that, this arrival of energy protons kind of sweeps away the cosmic rays. They don't reach the Earth anymore. And so you have a drop in quantity of cosmic rays arriving on the Earth. So that's another indicator. There is a network of counters and measuring neutrons around the world. This in particular is in Moscow. This was a network of neutron detectors that were put in during the Cold War to measure the nuclear explosions from the other side. But they can also form a useful network to study space weather. So that is triggering of this changing cosmic rays. And then finally, the disruption of the magnetic field of the Earth. So that's the magnetic field of the Earth measured by magnetometers. So these are instruments that measure the magnetic field. When the storm arrives, it disrupts the Earth's magnetic field. These disruptions can damage power lines and other electrical infrastructure and other type of infrastructure. So that's kind of a series of events that happens during a storm. This was a particularly strong one, but they more or less all have this series of events. First, the eruption of the sun, then a few days for them to arrive at the Earth, and then this reduction in cosmic rays and the disruption of the Earth magnetic field. So let's look at the event from the series of events. So you get this arrival cloud of plasma that compresses the magnetic field of the Earth more. So it pushes the bow shock and the magnetopoles closer to the Earth, and it disrupts the whole magnetosphere, producing this release of energy in the tail. And this release of energy in the tail tends to come towards the Earth. So here you see the high energy particles created in the tail and streaming towards the pole. Here is an eruption, disruption of the magnetic field of the Earth, and production of this cloud of electrons. These are primarily electrons that arrive at the Earth, and you see here the intensification of the polar light. You see a ring here, it's called auroral oval, because it's oval in shape over the pole, and it's called the aurora. So it's called the aurora oval, and it's seen from the ground in higher latitude. If you are in Sweden, Finland, or Alaska, or northern Russia, you can see this from the sky with your own naked eyes. And of course, the same happens on the South Pole. So that's a series of events. Here is brighter images of the blow up of this auroral region around the Earth. Now, the auroral region, when it's a very strong storm, can come down further, and it is very rarely, occasionally possible to see it from Belgium, but it is very unlikely. However, there are historical records that the aurora used to happen at lower latitudes. There is a story that there was a Roman emperor that noticed a bright light in the sky, and he thought that there was a fire in Rome. And he sent the soldiers to help put out the fire, but there was no fire. It was the aurora reaching all the way to Rome. I know in our modern days, it's not possible for an aurora to reach Rome. So that means that during the Roman time, 2,000 years ago, the magnetic field of the Earth must have been weaker, or there must have been a tremendously strong storm, because it's never heard now for centuries that the aurora arrives all the way down to Rome. So traditionally, these storms are subdivided in two classes. And the intention of the people that derived this classification was that a storm is made of many substorms. That's not true. It's wrong. Their understanding was mistaken, but the name stuck. So substorms are regular, common events. They happen all the time. It doesn't need to have a storm. So nothing peculiar is happening on the sun. There is no eruption, but still there are variations in the solar wind. And just because there is a small variation in the solar wind, that triggers some event around the Earth. So that's a small storm, let's say. We should really call them superstorm and small storm or something like that. But the name is substorm and substorm and storm. Storm is what we describe. So storm is a big event happening on the sun. It's very rare. It happens only during solar maximum. It can happen multiple times a day, but normally it happens a few times a month. And during solar minimum, it can happen every few months. It's very rare. And that's due to the cloud coming from the sun and impacting the Earth. Some storms instead are triggered by small changes in the magnetic field of the solar wind. For example, the magnetic field changes sign, or there is some other variation in the magnetic field of the solar wind or in the speed of the solar wind. For example, going from slow solar wind to fast solar wind, which is going to happen in 2 or 3 days, and they may very well trigger a substorm. These are small storms, nothing to worry about. Big storms instead are more important. But even substorms you need to know, because it may still impact the spacecraft communication, GPS systems. So it's something to monitor as well, but it's not going to kill anybody. Storms instead, can be dangerous for astronauts and destroy transformers and power lines and stuff like that. So it's much more serious. For this reason, there are these weather services. Let me just click to show you the European. The monitor space weather. That's the European system. As you can see here, they give you some information about the conditions right now. There are many services you can click on, and each one of these is a link that you can follow and get information about specific impacts of space weather, for example, for airlines, for power systems, space surveillance and radio communication and so forth. For all these activities, they tell you what is the impact of space weather. And then there are this expert center, and the expert center for heliospheric weather is in Brussels at the Royal Observatory. And the geomagnetic conditions is the Belgian Institute of Space Aeronomy. But there are also others. For example, the space radiation is solar weather, sorry. Solar weather is in Norway. So each one of these is a different European country, or not really European, member of ESA, European Space Agency, which includes also Norway, while Norway is not part of the European Union. So this is not the European Union, is ESA, European Space Agency, that has this, although most of the funding is coming from the European Union, but through ESA. Then there is the American one. Let me show you the American, which unfortunately, I must admit, much more sophisticated. They have been doing this for longer periods, and that's the American system that gives you that movie of the solar wind that I showed you earlier, and it gives you also many other pieces of information. And so their expectation is that there will be when we see this transition to slow solar wind, there's going to be some activity. But this is what they're showing in their prediction. So right now there is nothing really happening. This is very weak in yellow. It's only important when it becomes red. Here there is some activity happening here. It's not quite as quiet as the previous day, but not so much. A nice feature of the American system is this aurora forecast that tells you where the aurora is going to happen. It's very convenient if you want to go on travel to North Pole or something closer to the North Pole. Then you may want to use this one to see whether you are likely to see northern lights. So that's the American website. These are the two main